Okay, today we're going to look at vector basics. So we're going to look at vectors. All right, now vectors are really easy. They're a really easy quantity to look at. They're a quantity that have magnitude and direction. Okay, magnitude, and they've also got direction. That's a C. Okay, often we represent things that are vectors as arrows. So an arrow obviously has a direction, but the length of the arrow can represent its magnitude or how big the number is. Okay, its position doesn't matter. So I could draw the same vector over here, right? As long as it's going in the same direction and it has the same length, then it's the same vector. Okay. All right, so now we're going to get into a little bit of the notation. So I'm just going to quickly go through the different notation here. Okay, so we've got, I like to call the position notation or the directed line segments notation. It's when you've got a point on the plane, or a couple of points on the plane. So you could have, here's a plane, and you could have a point here, this is point A, and a point over here, this is point B, okay? And the vector joining those 2 points together, okay, we could draw an arrow from A to B, okay? So the length here would represent the magnitude of the vector, and obviously the direction is from A to B, okay? So we can write that as AB with an arrow on the top, okay? An arrow on the top means it's a vector from A to B. Okay, it gives us the direction like that with the arrow. It has as a vector. I'm really cool because I'm so awesome. I don't put the bottom arrow on. Okay, so you'll see that sometimes. Often in the textbook, it's just written with the proper arrow, but you can just do the half arrow, and that represents the vector as well. Same thing. Okay. You can also have column vectors. Okay, written in little 2x1 matrices, or different depending on how many dimensions the vector is in. So different number of rows per column. So a column vector. So if, for example, how should I do this? We could say that this vector here was 3 units across and 4 units up. We could write this vector as a column matrix 3, 4. Okay, so how far does it go to the left or right, and then how far does it go up or down, or how far does it go in the X direction, how far does it go in the Y direction, and if it was 3D, you could have another row here and say how many in the Z direction. Okay, you could also go to 4 dimensions and do the same thing. Okay, often though this is a bit cumbersome, so like we want to create this nice little shorthand, so we could just use, in the book they use a bolded single lowercase letter to represent, just so I want this vector to be A, yeah, but when you do it with freehand and in your exams you need to put the tilde underneath, okay, to represent the vector. So I've got the little tilde there. That's the other notation. Alright, what else do we have? Okay, now let's get into the actual calculations and things you can do with vectors. Okay, so we can look for the magnitude of the vector. So we've talked about vectors having a length or a magnitude, how big the number is. So how do you find that? Okay, so if you have a point on the plane, A, to be at, we'll make this at 3, 4. Okay, so let's draw that really quickly. Just do a little quick sketch. Okay, so we've got our origin here and our point, which is 3 units across and 4 units up. Okay, so there's my point A at coordinate 3, 4. Okay, so I want to find the vector, or the magnitude of the vector. Let's look for the magnitude of the vector OA. Okay, so OA, so from the origin to the point A, there's my vector OA. And if I am sick of writing that, I can call that just a letter. Let's call it A. So I'll call that A. Now to find the magnitude, now the way that we write that is we put it in what's called absolute value sign. Okay, O to A, there's my vector. So the absolute value of O to A is the same as the absolute value of A because that's how I've defined it. Okay, and the way you work that out is just, I want to know the length of the arrow. Okay, now the length of the arrow, we know that it's 3 across and 4 up. Oh, I haven't drawn that very well, but you get the idea. So I can picture this as a right angled triangle. So, well, what's the length of that side? Well, that's just using Pythagoras' theorem. Okay, so I can say that is going to equal how far in the x direction squared plus the y direction squared, take the square root. So let's do that really quickly. So I get 3 squared plus 4 squared, which is of course a 3, 4, 5 triangle. You could see it from the beginning, I'm sure. 9 plus 16, square root 25 is of course 5. 5 units. So the magnitude is always going to be a number, okay, because it's just how long that vector is or how big the vector is. It doesn't have to be a length necessarily, it's just easier geometrically to think in terms of lengths. Okay, so your magnitude is just the size of that vector, whether it's force or velocity or whatever. What else do we need to do? We need to do addition of vectors. So how do we add them up? Addition. Addition's really easy. Geometrically, we can take 2 vectors and add them up. So here's a vector u, here's a vector v. Okay, so what do they look like when you add them up? Okay, remember I said that they don't have position, so I can move this vector around to any position, and that's fine. Like, okay, so it will still stay the same. So I'm going to move this one, this v, onto the head of this one and draw it there. Same magnitude, same direction. Okay. Okay, so this is called adding them head to tail. So the head of the first vector goes to the tail of the second vector. So think about it as joining them up, joining up the arrows. So I start here, I walk along here, I join it up to this one. Where do I finish and where did I start? Okay, so the sum of those 2 vectors is just going to be, oh, oops, I haven't drawn that well. The start of the first vector to the end of the last one when you add them head to tail. Okay, so that's u plus v. Okay, and that's it. Okay, so if, you know, u was written as a column vector, so just say we had u was equal to 1, 2, and v was equal to, we'll make that half and negative 1, say. Okay, so when you add those vectors together, so u plus v, that's just putting the 1, 2, just doing the matrix addition here. Matrix addition, so you add the x's together, we get 1 plus a half, which is 3 halves, 2 minus 1, which is 1. Okay, so that's pretty easy. The column vectors make it very simple to do. What else do we need to do? Oh, scalar multiplication. So scalar multiplication. So you think of scalar multiplication as just scaling up or scaling down a vector. So if you have a vector u that looks like this, okay, if I wanted half u, so I'd want to go in the same direction but only want to go halfway. So half u is going to be this vector. That's half u. Half of u. Okay, that's all scalar multiplication is. You know, I could have doubled that vector So double the vector, make it twice as big. That's twice u, okay, but in the same direction. Okay, so I could scale it up or scale it down however much I want. If you had u was equal to 3, 4, if I wanted twice u, of course I'm just going to double the column vector here. So that's going to be 6 and 8. That's it. Okay, so that's scalar multiplication. Of course, you can also have the 0 vector. The 0 vector is just going to be 0 in both the columns. Okay, how do you draw a 0 vector? There we go. That's it. Little dot. Oh, it's got no magnitude, and obviously if you have no magnitude, you can't really have any direction either. Okay, so that's the 0 vector. I'll show you this. This is sort of the polygon notation. Polygons. So you could have polygon ABC. ABC is a triangle. So A, B, C. A, B, C. Okay. So here we go. Now, if we know this, if we're looking at addition, if vector AB, right, is going to be this vector along here with an arrow on the end, and then we add the vector BC, which is this vector here, they're added head to tail. Okay, so that's vector addition. So that's going to be the same as going from A to C. So that's this vector here. Okay, A to C. So this is a nice notation here because you're just going from A to B, from B to C is the same as going from A to C. Sorry. Okay, so it's like cancelling out these middle ones and putting those vectors together. When you write it like that, yeah, when those letters are the same in between, you're basically skipping over the B's and going straight to C, going the roundabout way. Okay, that's pretty much it there. All right, so how can we work out whether vectors are parallel or not? Okay, parallel vectors. Parallel vectors. Okay, vectors are parallel if you can write vector A as a scalar multiple of vector B. Okay, then if you can write them like this, then they're parallel. Okay, so if you've got vector A is equal to 3, 4, and vector B is equal to 12, 16, okay, then vector B is equal to 4 times vector A. Yeah, is that easy to see? So I can say vector B, which was 12, 16, is 4 times vector A, 3, 4. So 3 4s are 12, 4 4s are 16. Since you can write it as a scalar multiple, A and B must be parallel. A and B parallel. Cool. That easy? Surely that's easy. All right. How are we going? All right. Multiple dimensions. I mentioned this a little bit before, but if you just say you're looking at a three-dimensional vector, x, y, z, and you're trying to find, say, the magnitude. So the magnitude of u, you can just extend that Pythagorean theorem, x squared plus y squared plus z squared, which is very nice. So that's very easy. So all the stuff we've learnt so far applies in different dimensions. So we don't have to just keep it in 2 dimensions. You know, we can go to 3 or 4 or 5 dimensions if we wish. All the same maths applies, which is lovely. Okay, so what do? They commute. So vectors commute. What does that mean? You know, they commute in terms of addition, they commute. So A plus B is equal to B plus A. So it doesn't matter what order you add them in, they're the same thing. when you're talking about addition, they associate, the associative law. So that just means if you've got, I should put my vector tildes underneath here, otherwise I'd lose all my marks, plus C equals to A plus B plus C. So it doesn't matter if you group these ones together and add them first and then add that one, or you group these ones together first and then add that one, they're the same. And they distribute. Now distribute, it's really nice. So if you've got m of A plus B, that equals m times A, where m's a scalar, and the A's and the B's are vectors. A, B. So you can, expand the brackets. This is really great because all that algebra you've learnt in year 7, 8, 9, and 10, and 11 still applies. Okay. All right, let's do a couple of little examples. Okay, if let's say O, A, B, C is a tetrahedron. The first platonic solid. What a great shape the tetrahedron is. Okay, so I'm going to draw a tetrahedron here. So here's this face here, and I'm going to draw. Okay, so I'm going to call this O, A, I'll call this one B, and C. Okay, see my tetrahedron sitting there. Perfect. So if I call OA, so I'm going to call OAA, like that, OAA. OB, I'm going to call that little b. And then OC, I'm going to call that little c. Okay. Can I write AC in terms of A, B, and C? Okay, so what is AC equal? So I want to go from A to C. Well, I only want to go along these paths that I've already got defined so far. Well, that's easy. I can go from A, instead of just going A to C, I go A to O, and then O to C. Okay, that gets me from A to C. So I go A to O plus O to C. Okay, so that's easy. That's like the polygon shape we did before. Now A to O, well, the O to A is positive A, so A to O is just the negative of A, because I'm going the opposite direction to that vector. The directions are important, so negative A plus O to C. Now O to C is just C, so I can rewrite this in another order. Remember, they commute, so that's fine. So I can write that C minus A. Perfect. A to C. All right, what if I wanted to find M is going to be the midpoint on A to C. Okay, so the midpoint here. And I wanted to find O to M. So what's O to M going to be? Okay, so I'm starting at O and I've got to finish at M. So I want to go from O to A plus A to M. Okay, so O to A plus A to M. Okay, now I'm going to change notations because I know O to A is just A. And then A to M, well, that's halfway A to C. Now we just found A to C up here. Okay, so half of A to C. Okay, so I've got A plus 1/2 of A to C, which is just C minus A. Perfect. Plus half, expand it, distribute, minus half A. Add up like terms, I've got A minus half A, that's just half A, and then plus half C. And then I can just write it as half of A plus C. Perfect. Okay, that's lovely. All right, we've got that. Now we've got that. Just got one more example to do, and this is the main bit of this first chapter, is linear dependence and independence. Okay, so vectors are, if they're linear independent or linear independent or dependent? Okay, so the easy way to think of this, just say I have three vectors. So I've got vector A, vector B, and vector C. Let's do vector C like that. So if in 2D, it's easy to understand this in 2 dimensions, can I write vector A, say, as a linear combination of these two vectors? So can I stretch this one out and stretch this one out so I can get them to add up and be equal to A? So what I'm asking is, can vector A be, if I have a number, if I stretch out B and stretch out, or shrink or stretch out C by another, can I get it to equal A? Now, as long as none of these are parallel, they're always going to be dependent. That means I can do that. They're linear dependent if I can do this. Okay. Now, so if I'm trying to think of what this means, if I stretch out, start with B, if I stretch it out a bit, yeah, that's my stretched out B, and I stretch out C enough, and C, then I'm going to be able to, that's my B, that's my C, I'm going to be able to get my vector A. Okay. Alright, now I haven't drawn that very well, but you get the idea that a combination of these, either stretched out or shrunk, can give me that vector. Okay, so that's linear dependence. If you can't do that, then the vectors are linearly independent. Okay, alright, so let's do an example here. Just say I have some column vectors. I'm going to write these as column vectors, make it easy to understand with the numbers. So I have column vectors 1, 1, negative 1, and B 3, negative 1, 4, and C is going to be 3, negative 5, 11. Okay, so can I write A? Can A be written as a scalar multiple of B plus a scalar multiple of C? Okay, can that happen? Are they dependent or independent? If you can't do it, then they're independent. If you can do it, then they're dependent. Okay, so if I write that out, I've got 1, 1, negative 1 equals M 3, negative 1, 4 plus N 3, negative 5, 11. Okay, now I could split these up because M is going to multiply by all of these and N is going to multiply by all of them. So let's split it up into some nice easy equations. So I'll take the top bit of each line here. So 1 is going to equal 3 times M, and 3 times N. Okay, that's my equation 1. Equation 2, look at the second one, second row. So I've got 1 again equals negative M minus 5N. And then lastly, I've got negative 1 equals 4M plus 11N. Okay, so this is equation 2, and this is equation 3. Alright, so I'm going to try and solve these simultaneously. So I've got two equations here with two unknowns. Okay, so let's rearrange this for M, this first one. So if I take out the 3, I get 1/3 of M plus N, and then, I get 3 times M plus N, and then I divide by 3, I get 1/3 equals M plus N. Okay, so ran out of spot here. So I've got 1/3 equals M plus N. That's from equation 1 here, dividing both sides by 3. So then I could have M equals 1/3 minus N. Okay, I can have that. And then I'll substitute it into this equation. So now I've got 1 equals negative M. So that's going to make that flipped around the other way. So I'm going to have N minus 1/3 minus 5N. Okay, so then I get 1 equals N minus 5N minus 4n minus 1/3. Okay, now I can solve for n here. So I can add 1/3 to both sides. So 1 plus 1/3 is 4/3. Yeah, 3 on 3 plus 1 on 3 is 4 on 3. Minus 4n. Cancel out the 4's here. Divide both sides by 4. Take the negative across. I get n equals negative 1/3. Okay. Now if n equals negative 1/3, what does m equal? I've got 1/3 minus minus 1/3. So minus a minus is plus. So I've got m equals 1/3 plus another 1/3, which is 2/3. So there I've got my values for m and n. But I just have to make sure that it's going to satisfy this. If it satisfies the last equation, both of these solutions, then we've got linearly dependent. If it doesn't work with this equation, then these are independent. Okay, so let's try. Negative 1 is the left-hand side. Does that equal 4 times m, which is 2/3, plus 11 times n, which is negative 1/3. So what do I get here? I get 8/3 minus 11/3 equals negative 3/3, which equals negative 1. Okay, so the left-hand side is equal to the right-hand side, QED, linearly dependent. Okay, and that's it for the first video. Well done.